at the moment, we're actually just leaving this part of Iceland, and this is the oldest part of Iceland. We've just actually been in the safe part of Iceland, where no volcanic eruptions have occurred in some 10 million years. And the red zone here on the map, that's the dangerous part. That's where the active volcanoes are. And this is where the spreading ridge of the Atlantic is actually popping up on shore. And here you see that in this image here. And I'll skip some of the details. I'll just point out the really relevant features. But in this map here, you see the elevation is changing, and this is the spreading ridge. And Iceland pops up above sea level, and the ridge here, the red area, is where the active volcanoes are. Now, why is it that Iceland just pops up and not the entire spreading ridge of the Atlantic? Well, I'll talk more about this tomorrow, but there is what we call a hot spot underneath. It's the same thing that we find under Hawaii, and the hot spot just happens to coincide with the spreading ridge of the Atlantic. So it's two things coming together, making Iceland very special. And this is why we can see the Atlantic spreading ridge above sea level, and that allows us to see all these features here on Iceland. So, but I'd like to take you to the Reykjanes Peninsula, and well, here's Reykjavik, and this is the Reykjanes Peninsula, and there's Reykyanes here at the very tip of it. And as you see already here in this satellite image, there's stripy patterns in the rocks here. And this is important because here, all the volcanoes picked out in purple here, they have these stripy patterns, and that's meaningful to geologists. It means there is a strike-slip component, as we call it. It's not just spreading laterally, it's actually shearing against each other. And we call that a leaky transform fault. Well, never mind the details. What it means is it's not just drifting apart, it's more complicated than that. And when it does slip against each other, little gaps open up in the rock, and this is where magma can rise up. So, but having talked about the Reykjanes, I must tell you something, and that is there was no eruptions on the Reykjanes Peninsula for something like 800 years. So here's the different volcanoes, and the volcano we are talking about has a very complicated name. It's the Fagradalsfjall, and this one has not erupted for several thousand years. All the other volcanoes have had a gap of some 800 years, and then they had these periods of eruption for several tens of years or hundreds of years. Then there was another gap here, and back round about the beginning of our time measurement, there was a period of eruptions, and then there was one about 1,000 years before we started reckoning in time. And each time, all the volcanoes got active, and then they paused again, and they got active again, and then they paused again. And this is what worries us, because now the first one has started again. I'll talk about this a little more at the end of the presentation, but let's go into the eruption first of all. Let's see what happens. So, it all started in December 2019, and into March 2021, there was more earthquakes than usual, and some of the earthquakes were quite big, and some of them were 5.6 on the Richter scale, and that's really kind of intense. This is when cups fall off the shelves. And then in the 3 weeks before the eruption began, 40,000 little earthquakes occurred. Really, a lot of them. And of course, the seismographs got mad, so people in Iceland knew something is in the bush. And on 19th of March, an effusive eruption started at 8:45 p.m., and it was in a little place called Geldingadalia. Thankfully, nobody lives there, so nobody was really immediately in danger. So the eruption was first announced by the Icelandic Meteorological Office at 9:40. It took them only an hour to recognize what's going on, and then there was a fissure opening up, a crack in the earth, and it was several hundred meters long, and it began to emit lava. And this went on into April, and in April, suddenly more craters opened up, the eruption got more intense, and the lava outpouring increased. So this is from the 20th of March, the first day of the eruption, and you see the fresh lava going over the soil and the moss, and burning up the moss, and covering the area here. And this is a time lapse, and I hope it works. It's for the first few days of the eruption. Let's see. So, and here you see how the lava is filling it up, and, well, it's day and night and day and night, so I'm not going to run it entirely. It's 3 minutes long, but you see how quickly it goes. And there's a bit of rain every now and then, of course, it's Iceland. So you see the valley is filling up really rapidly, and then, of course, ultimately, the valley was full. The lava was flowing into the neighboring valleys. So this is how it started. Here's our series of vents on this map in this remote valley, the Geldingadalur Valley, and here's this series of vents, little triangles marked on this map, and the vents were active at different times, but as so often, one of the vents was more prolific than the others, and it was vent number 5 that eventually took over and hijacked the entire eruption. Eventually, all the activity was focused on this one vent number 5. So this is an initial image of the fissure, the fracture that opened up. Here you see the fracture spewing out lava. And here you see the fissure again, but now several individual vents have formed. And eventually one of the vents was the strongest. As I said, this is vent number 2. And here's a little helicopter for scale. This is vent number 3. This is also vent number 3. And this is how it looked early in the eruption. This is the fissure, and this is vent number 5 at the beginning or early in the eruption, and this is the one that will take over. And you see vent number 1, the oldest of the vents, was of course very big early in the eruption. Vent number 2 was furthest away, so they were jumping around, they weren't sequential, very interesting phenomenon. And eventually vent number 5 grew that big. So, and this is vent number 1, let me bring you back. This was vent number 1 to start with, vent number 5 to start with, and at the end it looked like this. So this chap really grew extremely strong, and it's a little small down here. I'll run you through this. At the beginning of the eruption, the topography was about 200 meters above sea level. At the end of the eruption, vent number 5 was close to 350 meters above sea level. So the vent grew by almost 150 meters over the course of the eruption. So here's vent number 5, and this is also a video. Let's see if I get this to work. And this is a friend from the university in Iceland. The Icelanders are fearless when it comes to volcanoes. So this gives you an impression, and this was beautiful for volcanologists because you could actually look into the vent, you could really look into the volcano. It was a reasonably harmless eruption, and it allowed people to get very close. It allowed us with cameras and other instruments to get very close. And here is a view into the vent itself, and I ask you to watch this part of the wall. So we call this an intra-vent collapse, and so vents build up and they actually collapse into themselves. And to see these phenomena is very spectacular for volcanologists to understand the dynamics of volcanoes. So eventually the vent grew so big that it developed a pond, a lava lake on top, and the lava lake then grew bigger, and then it calmed down and grew bigger, and it calmed down, and by May, June, it actually had developed a rhythm. Very peculiar phenomena, and it erupted a little, and then it encrusted, and then it erupted again. So here's a very short time sequence, which one of my PhD students did, and this is at 4:49 p.m., and here you see the vent, and it's rising, the lava lake is rising for 55, just 6 minutes later, and then again, half a minute later, it was flowing over, and then it calmed down again. And then it took just a few minutes for the same process to start again. very peculiar, and we really kind of could measure the volcano's rhythm. You could feel the pulse of the volcano. And we have just published an article trying to explain why it's pulsing like this. We believe it has to do with how gas comes from depth, and here we're learning a lot about how volcanoes work internally. Another feature that was really interesting was lava pools or ponds that formed, and here you see a vent from above, and here you see a lava pool, and yeah, they have these little compression ridges that form on the surface. The surface cools, it's a bit like the skin on hot chocolate, and when you blow it a little bit, it sort of forms these wrinkles, and this is what we see here. It's the same on lava, only lava is a little hotter. So here's one of these lava pools, and here's another one, and various pools existed over the time of the eruption. Here's the scale. This is about 1 kilometer, the entire scale. And then, of course, volcanologists love to count things, so we have the first pool, and the second pool, and the third pool, and this was changing over the course of the eruption. And nowadays with the drones, we get these spectacular images. This was also by one of the PhD students. He flew the drone right over the vent, and here you see a little bit of magma coming up. This is the intra-vent, and there you see the lava hardening and encrusting. And it was only like this for a few minutes, and then a new pulse would come and destroy the skin that had formed. Now, as I said, the lava was pouring out. Eventually, the valleys were filling up, and there was lava spilling into new valleys. And this was an intriguing phenomenon. Here you see there was contribution from various lava lobes and tongues coming together again, and they were filling up these valleys. Initially, we had an extent of about a kilometer or so. This is the 1404. And then a little later, you can't see the date here, but this was in June, the lava had spilled into Meradalia and also here to the south into Nathagi, so the night pastures as it's called. And there you could see how it started to go down into this new valley. This is this one here, Nathagi, and this is also something that, of course, we recorded in time-lapse. And again, I have a video here. Let's see if it works. It does. So this is the cause of a few days once the lava came in. And see how the lava inflates? It's actually not new lava on top. It's lava pushed into the interior of the lava flow, so the lava flow inflates. So, and eventually the eruption stopped, but here's a map with a thickness of the lava, and the purple colors mean it's very thick, and the lighter colors, the sand colors, means it's kind of thin. And here we have thicknesses of above 100 meters of lava and ash and scoria deposits. Scoria is the somewhat coarser particle that are beyond ash size. And down here, the furthest away, it was a little thinner. It was only tens of meters. But up here were the vents where we had hundreds of meters of new material. So I should point out, this is actually the volcano, Fagradalsfjall, and here was a flank eruption of the volcano that filled all of these. It's a flat-topped volcano. It's not one of those pointy ones, because it initially formed under ice and then they become flat-topped. This is why most people didn't actually recognize it as a volcano at the time of the eruption. So then humans have to interact with volcanoes, and I'll talk a little more about this now. And here, the civil protection authorities, they got really worried about certain things, and one of them was cables, fibers, water lines. And they started to do some experiment. They dug some ditches, and they put certain cables, fiber cables, into these ditches, covered them, and waited for the lava to run over them. And then later, they were testing if the cables still work. So this was a very useful experiment, and unfortunately, not all the cables worked. So it's useful to know which ones will survive and which one will not. Another feature that was interesting is that because there's risk that the lavas could extend all the way to the coast, and there was big roads that were endangered, people started to build these dams, lava dams, in order to stop the lava. So human efforts are often dwarfed by these natural events, and indeed, if the lava is very slow, the dams work. If the lava comes with full speed, the dams have no real consequence. So there was initial success with these dams, but eventually, when the lava comes in full strength, they are, of course, overrun. The volcano then stopped in September, 2nd of September, and nothing happened for almost a year. And then people realized that the volcano was good for a lot of things. The volcano was good for tourism. It was COVID, and Iceland, of course, is living off tourism and fisheries, and they realized the volcano brought a lot of people and brought a lot of money, and then there was almost sadness about no volcano erupting. So all the Icelanders went to church and prayed, I don't know, but maybe. And indeed, less than a year later, it restarted in August 22 in the neighboring valley, and that was Meradalia. And this is Meradalia, and this is when the colleagues in Iceland then called for support from international scientists, and so I had my chance to face Chakar, the lava monster, as we call it. And I was not the only one. The first day of the eruption, believe it or not, saw already 10,000 people watching the eruption. So tourism was back on for the Icelanders. So the 22 eruption, very interesting little eruption, and this is a satellite image. The satellite flies over the area repeatedly and measures it, and there you see subtle changes in the surface, and it gives you these fringes. It's a bit like oil on water, and it tells the scientists what's going on, and you see there was ground deformation already in the days prior to the eruption and during the eruption. And the lava was flowing mainly in the valley of Meradalia, and it was a very short-lived eruption, only about 3 weeks or so. And this is the map of the 2021 eruption, and this is the 2022 eruption, which happened to start here. Maybe you can see there's a dark red line here. This was as well a fissure, a crack that opened up, and that was pouring out lava, and the lava was going down here. And it was a much smaller eruption in terms of areal extent, but in terms of volume, it was actually quite respectable. So it started here with that fissure, as I said, and you see the fissure was cracking up the mountain here. So it's not the lava flowing up the mountain. That doesn't work, although it looks like it. It's the fissure that cracked up the mountain. And again, we saw the same phenomena. Initially, the lava was outpouring on the entire length of the fissure, but eventually, here in the middle of the fissure, one vent grew really strong. And this is my colleague, Arianna Soldati. She has just been appointed on the faculty in Raleigh, and she has been helping me out there. And here, this is the fissure. We're just looking at the fissure, and this was actually the first blob of lava on the fissure that came up, and we were able to go and collect a sample here. So here you see, I marked it in red, here you see the fissure, and eventually the volcano grew over there, and the crack on the hillside was still there. For us, it didn't get covered, so we actually had the opportunity to look at the very first lava, and of course later also at the very last lava of the eruption. And this is exactly where the eruption started. You can look into the little hole here, believe it or not. Here is a shoe for scale. So, and as I said, eventually this area of the fissure grew stronger and stronger. This area here where we've just been, this died out. And this is me posing, doing a selfie. And here you see the volcano, August 10th, about a week into the eruption. And this is me doing another selfie, August 12th. But don't mind me, look at the volcano, please. And you see the volcano is growing. Look, initially the fissure here was very small, and it was all rather even. And now the volcano is growing bigger and bigger. And this is August 13th, and this is August 15th. And you see how the volcano is building up. And this is August 15th. And now the volcano has become a respectable little volcano with an outflow here where the lava was draining the edifice of the new volcano. And again, this is a video, and it was done by one of my colleagues. This is a flyover of the eruption August 17th, and here the volcano has reached quite some size by now. So let's talk a little bit more about the eruption and what geologists do. And here again we have one of these maps that gives lava thickness. And up here where the vent area was, we have the highest thickness, over 40 meters. Down here in the valleys we have much lower thickness, only a few meters. Intriguingly, as I said earlier, the lava was flowing over the lava of the previous year. And this is something that really got us interested. This is something you see very rarely, and we really studied that in detail. So let me quickly bring you to this point here. This is where the Meradalia, the 22 lava, had its furthest extent. It was flowing over new ground. There was no lava underlying it from the previous year. And here you see the substrate, and here's the new lava. And of course, some of the blocks from the substrate were picked up by the lava. Here we have the 2021 lava, just in the days when the eruption had already started, but the lava had not yet arrived. So, and here the new lava is coming in. So this is where I was just standing, and this is the new lava creeping in bit by bit, unstoppably. And here we have also the vent up there. We have the new lava creeping up the valley. And then, of course, all the vegetation will start to burn. And it's an awful smell. And there's nothing you can do. And all the animals escape, of course. But this is how it is. So, eventually, I'm going to bring you to this point down here, the furthest distance from the vent the 22 lava was flowing to, and this is here. And here we see the 21 lava being broken up from the pressure of the new lava, and the new lava is the dark material here, and the vent is just up there in the far distance. So let me bring you a little closer. So this is broken up 2021 lava with new lava pushing from behind. Very intriguing phenomenon. And this is broken up bits and bobs from the lava of 2021. And the good thing about this is you can actually look inside the lava now. And here we have the surface, the ropey surface. And what we see in here is a lot of vesicles, a lot of bubbles, gas bubbles. And here's another one, very large. And this is actually the secret why lavas can inflate. There's new lava flowing into, but there's also degassing. As long as the lava is still hot, the lava will push its top upwards. This is why it's very dangerous to walk on fresh lava. You could crack through. So now I talk for a few minutes about what we actually do there. Geologists, they run around, and we have a bad reputation usually. We run around with hammers, and in the evening we drink a lot of beer. It's not quite so simple. I'm going to tell you a little bit about the trade secrets of geologists now. And what we do is we study the rocks. So there is a lot of different rock types out there. Basaltic lava, this means lava with a silica content of about 50%. It's the black material, but also there's glassy material there. And then, of course, there's liquid runny lava. If it runs really nicely, it's called pahoehoe lava. It's a Hawaiian term meaning smooth lava. And then when it cools, it becomes blocky, aa lava, lava that is made of large blocks. And then, of course, there's pyroclastic material. And pyroclastic means pyro is fire, clastic is broken, fire-broken material. And this is ash and what we also call lapilli, small stones. So here's the different rock types that we see. And this is the lava, liquid lava, solid lava, and material that comes from fire fountains, broken up material. And the most beautiful rock of the entire eruption was this, which the local people called the golden pumice. And chemically, we analyzed it. It was exactly the same as the black lava. And people were asking frequently, how can this be? How can it be golden while it has the same composition as the black material? And the simple answer is, it's like Coca-Cola. So here you have the golden foam and the dark Coca-Cola. And this is frothed up vesicular material, and it looks to us golden, but chemically it's identical to the other material. So now lava rocks, and here this is now how geologists engage the lava monster, as we often refer to it. And here we have different rock types, and here we have glassy material, here we have flow-banded Pahoi material. And in order to sample rock, you need a lot of complicated equipment. So this is the geologist starting pack. And then you have this in the field, and usually it looks much more organized before you go to the field. In the field, you have to go through your bags and find all the right things. So having prepared myself here with a gas mask and all these things, I then have to do a little check on the lava. So you need a gas meter, you need a thermometer, you need a hammer, you need the goggles, you need a gas mask. And once you have all this, you have to check how the wind is going, how much the gas is, and your gas meter will tell you what is your escape routes. And once all of this is done, you measure the temperature, and eventually, if it's cold enough, you can just go and take a sample. So here's Professor Ariana and myself taking a sample on cold lava. That's the easiest way of doing it. Now, it gets a bit more complicated if the lava is runny, but if it's an open space and the lava is thin, it's still relatively easy. You can go and scoop it up. So, if it's in valleys and the lava is thick, it's a bit more complicated. Again, you need to do all your measurements, and eventually you cool some bits down that you have separated from the main lava. And you always have to have your gas meter here, because one of the most common deaths of volcanologists is to actually be in gas traps in valleys. And CO2, for example, and CO is very dense. It collects in the valleys. And this is where you suddenly run out of oxygen, potentially. So the little gas meter tells you when to get out. It starts beeping really annoyingly, and then you know it's not a good place to be. So eventually you have a rock sample, and this one is still a little warm, so we have these thermal gloves that allows you to actually work with these things. The thicker the lava gets and the more runny it gets, the more dangerous it gets, and then it becomes less easy. It actually becomes quite dangerous. You need increasing amounts of protective gear, and the most complicated sampling is actually to sample liquid lava itself. And maybe you've seen some of the footage from Hawaii. Some of the colleagues in Hawaii, they're very experienced. They have loads of eruption there. In Iceland, it's not quite so common. So this is challenging, as I said. And again, you have to check how runny is it inside. You measure your temperature, because it's different on the outside and the inside. And, well, you have to think first. You look at it for half an hour and you think, what's your escape route? What is the gas content? What is the quench options, etc. And then all your friends make all sorts of suggestions, and you kind of go, no, not a good idea, I don't like this. And eventually you go there and you have a plan, and then you're ready, and then you take a sample. And here, this is also a video. Let's see if I get it to work. So, and this is something then we do on a daily basis throughout the entire eruption. And eventually we collected 150 samples, and it was quite a job, and one is really exhausted after a while. So, why do we do all this? Why do we go through all this misery? And this is why we do it. Here is our map of all the samples. We have samples from all the places, and this is our geochemical diagrams. And I'll spare you all the details, it's not so important, but we have samples throughout the entire eruption, and we can see what changes have occurred. And believe it or not, just when the new vents came up, when vent 5 became very strong, we also see a change in the chemical signal. So it allows us to determine that new magma was coming up at that point, changing everything. So we learned a lot about the internal workings of the volcano by doing this time series sampling, which was quite a job, but it was worth every bit of it. So, and of course, scientists are always in competition. So here's our model. And this is, of course, nice and complicated and explains everything. This is the model of the competition, which is much simpler and therefore less sophisticated, I'd like to think. But, of course, both groups have determined the principal features here. And this allows us to now say where the magma comes from, what contributions are made from depth, how the magma is rising up, and how it's changing with time during the eruption. So, for the last few minutes, I'm going to talk now about this problem, and that's very important to me to bring across to you, and that is natural hazards are not automatically disasters. Natural hazards are only disasters if we ignore our vulnerability. It's very important that I bring this to everybody, really. Natural disasters and vulnerability. That's what makes disasters. So, these lava flows, they were happening in this area here. They have not done any serious damage, and that's good. But are we vulnerable to damage in the future? And of course we are. And this is something the Icelandic Civil Protection is thinking about very carefully at this point. I should point out Keflavik Airport is here, and Reykjavik is here, and then there's the town of Grindavik down here. So these are all areas that are in the problem zone. Here we have the lava field. Here we have a road down here. And if the lava had spilled a little further, this main road here between Erabagi and Grindavik would have been cut off. On top of that, this is the Blue Lagoon, the biggest tourist attraction in Iceland. And it's next to the power plant that gives electricity to Keflavik Airport. And we're very close to the eruption site here. And this is Grindavik, the town of Grindavik, which is also pretty close. All these brown areas are lava rocks, and there's more lava rocks here. So if new vents open up anywhere in that area, this could become a little bit of a headache. And Keflavik Airport is the largest international airport in all of Iceland. And, well, it's not so far away from the eruption site. And not only could there be problems for air traffic on a short-term basis, here's the eruption cloud that came up, and here's on another day the eruption cloud, and here you see the stem, and there's a bit of a water reaction in the air, and this could be problematic. Some flights might need to be cancelled, but that would be the smallest of problems. The much bigger problem is here, these episodes of eruptions that lasted several tens to hundreds of years, and they are clearly a repetitive feature. There was one back 1000 BC, then around Christ's birth there was one episode, there was one round about the year 1000, and now a new volcano has started here. So there could be a whole series of new eruptions coming up on the Reykjanes, and we have to be really prepared. All these purple rocks here are lava eruptions, historical lava eruptions. Some of them were going even to the north shore. Some of them reached the outskirts of what's today Reykjavik, and therefore no road in the area is actually safe if this new episode of eruption starts. And even Reykjavik may not be entirely safe. So this is a big concern, and here's some footage. It's a little blurry because it's a very complicated photo, but you see the 400-meter tall eruption column from 2021. It was visible from Reykjavik. That gives you a sense of the proximity. So the problem is, you could argue, well, there's more airports. And it's true, there is more airports. There's one in Akureyri and one over here in eastern Iceland, but they're all much smaller and they're far away from Reykjavik. If we had to develop an air bridge to supply Reykjavik, it would be very complicated. It would be really logistically a bit of a nightmare. So I'd like to thank you for this, and let's just hope that the Reykjanes will calm down again, because it could actually be really expensive for Iceland, and the income from tourism might not make up for the damages that could be causing. Thank you very much for your time.